So now let us see that if we have a gas inside a tube, cylindrical tube, which is rotated, then how the pressure varies with the radial distance. So here we have a tube and it is filled with a gas and it is rotating with omega angular velocity. The pressure at the axis is P naught. So we want to see how the pressure varies under isothermal conditions. So isothermal conditions is there. Isothermal conditions prevail. So what we do at a distance r from the rotation axis, let us consider an element. So this element, so here suppose pressure is P. So P into area of cross section is the force, and suppose from this side, suppose pressure varies, so P plus dP is the pressure into area, and the total mass of gas in this element is dm omega square r is the centrifugal force acting on this. So now consider the equilibrium of a thin slice of air. So PA force is from this side, that plus dm omega square r is equal to P plus dP into A. So these terms cancel. dm mass is equal to rho A into dr, omega square is dP into A. Again A cancel. So rho omega square r dr is dP, that is equation number 1. This is the relation number 1. We have related change in pressure dP with dr. We want to know rho. So using ideal gas law, that is P by rho is equal to RT by M, implies here rho will be equal to PM by RT. So this is the second relation, we will put this here. So from 1 and 2 we get rho is equal to PM by RT. R is gas constant, T is temperature, omega square R dr is equal to dP. So I will bring P this side. So implies omega square R m omega square R by RT dr, that will be equal to dP by P. So integrating both sides with pressure here as P naught on the axis and pressure at here P, radius is here 0 to R. So this on integration gives m omega square by RT. R dr means R square by 2. You will have R square by 2 equal to, this is log ln P, that from P naught to P. So again this is ln P by P naught is equal to m omega square R square by 2RT. This is the relation. So finally let us see, this P will be equal to P naught times e to the power m omega square R square by 2RT. This is how the pressure will vary with the radial distance in a rotating cylinder. So now let us take an example of Boyle's law. So it's unusual, let us take a unusual piston. So we have a special vessel in which the cross section is varying. So here cross section is different and here cross section is different, and we have a piston here, two pistons, one here and another one here. The two pistons are connected by a string and their combined mass is m. So combined mass of the piston is m. So inside this we have an ideal gas contained. This is n moles of ideal gas inside is there, and the outer, here outside we have atmospheric pressure as P naught. So P naught is the atmospheric pressure outside. This is open, this vessel is open, so it's not a diathermic ball. So we are going to increase the temperature of this gas. So how should we increase, by what amount we should increase so that the piston moves L distance up? So how much should we increase the temperature of the gas? Of course by heating from outside by the gas, so that the piston moves by L distance upward. This is what we have to do. So you see here, suppose the piston moves upward. If we heat, the piston may move upward, may move downward. That we have to find why it moves upward. Now suppose if it moves upward, then there is a increment in this volume, but there is a decrement in this volume. So suppose this area is S2, LS2 will be decrement and LS1 will be the increment in volume. So there is a total net increment in volume. So since we are increasing the temperature, its volume should increase, so it will go up. If we decrease the temperature, then its volume should decrease according to Boyle's law, then it should come down. So if we have to move these pistons up, we have to increase according to Boyle's law. So that the piston moves by L. So now you see, let us consider the equilibrium of this piston, the total force acting from here, and this is the tension T. So consider the equilibrium of the upper piston. So total force P naught A from upward plus M1G, weight of this piston M1G downward, plus tension is equal to P into S1. S1 is the area of the upper piston. Now it is given that, so the difference of the piston cross section is delta S. This is a given quantity. So this area has S1 and this area is S2. So this is equation number 1. Also consider the equilibrium of the lower piston. So you see here, P naught A is the force, P naught into S2, and here is P naught, internal pressure is P. So this P into S2 is the pressure from here, and the weight is acting here and the tension is acting here. So the total force is here, don't write A, here also S1. So now consider the equilibrium of the lower piston. Total upward force you can see here is P naught S2. Then it is plus T, and this is equal to total downward force, that is PS2 and plus M2G. So we can bring this M2 this side. So when we bring this M2 this side, then I will write here this, we can write then here only I am writing, then minus M2G is equal to PS2. So we bring this M2G this side. So now we have two equations. So subtracting 2 from 1. So you see, if I subtract, then you see it will be P naught S1 minus S2. These tensions will cancel out, these masses will add up, M1 plus M2G, that is the total piston mass, that is PS1 minus S2. So now you see here, this P we got, this P naught into delta S plus total mg is equal to P into delta S. So we got the total pressure as inside this as P as P naught plus mg by delta S. This is the pressure of the gas inside this. Now you see this pressure is P naught plus mg by delta S. So now you see here that here we will write PV is equal to nRT. So here you see the pressure does not vary. The pressure does not vary. So you see this V will be proportional to T. So it is actually not Boyle's law, it is Charles' law, application of Charles' law. You can see that at constant pressure, you see this is isobaric process. Pressure is constant throughout the process. Pressure does not change. So volume will be proportional to delta T. So what we will do now, so we require, this is P is constant, I require delta T, that is equal to P into delta V by number of moles into R. P we will put from here, that is P naught plus mg by delta S into delta V, change in volume. So if I move L distance, my increment in volume is L S1, L times S1, and the decrement in volume is L S2. So this is total change by NR. So delta T becomes P naught plus mg by delta S into L, this is S1 minus L2, again L delta S by NR. So you see here, this is the increment in the temperature of the gas inside that should be done in order to move these pistons L distance. So here everything works on the principle of Charles' law, according to which if at constant pressure the volume will be proportional to temperature, that is the change in volume will be also proportional to temperature.